All right, and now I'd like to convene our last session. And organizers are Lin Liu, who's a professor of chemical engineering at Princeton University, and Tina Ng, who's a senior research scientist at Palo Alto Research Center. I'd like to turn the podium over to them.
Good morning, everyone. So for today, before we go into the frontier and challenges of flexible electronic, Lynn and I have prepared some slides to give you the background on what has been done and how this field gets started and the new research capability that has been developed with this new tool. Please. So in this field, actually, it started with a materials discovery in 1976 in the field of organic polymer. So as you all know, conventionally polymers, it's an insulator, and we know that from everyday experience when you use a wire and that's covered by plastic, so you won't get an electrical shock. But then in 1976, 3 researchers were able to dope the polymer that they tune it from an electrical insulator into a semiconductor and then even into a metallic conductor that is electrically active. This is a really exciting and surprising effect because in the end, now they are able to tune electronic property in a synthetic material. And that's why they won the Nobel Prize in year 2000. So since then, since this discovery, researchers have been active in developing electronic device using this plastic semiconductor and conductors. The reason is that you can imagine with this new mechanical flexibility, they can demonstrate so much more capability than conventional silicon electronics. So the earliest prototype they have done is in the area of displays, large area displays and sensors. So you see there's a bendable display that's very robust and sensors that can conform onto a banded radius. So now you have really sensitive sensing capability. And in terms of materials lightweightness. Some of the work has been done to develop photovoltaics on textile so that you can have a lightweight solar cell that can be deployed in remote areas where power infrastructure is not there. And recently, in the past few years, you might have seen in electronic shows, we actually are starting to commercialize this material in the OLED business with cell phone, mobile displays. But this area is very active still, and now there's more material choices than ever, and our speakers will speak to that. So now we have flexible electronic that can even be dissolved. And then they have developed stretchable electronic that imitates skin. And lastly, recently we saw work on self-healing polymer where if you have a cut in it, it could self-repair and reconnect and become electronically active again. So this exciting development, could you go to the next slide? So this exciting development is enabled by both these 3 major areas, and you can imagine it incorporate knowledge from all these different disciplines, from fundamental material study that learn how to engineer robust and electrically tunable materials to new processing technology. For example, we show here a picture of additive printing, so we can go beyond conventional fabrication techniques and fabricate electronic on curved surface, on digital processing strategies. And then lastly, with new devices, people have been inspired to develop new applications in bioelectronic ubiquitous sensing networks. And so our speaker will touch on all three aspects and the challenges associated with this. And as you listen to the talk, we hope that you will be inspired to think about how to incorporate flexible electronic in your research. Really, it helps in allowing a new form factor. You can potentially integrate electronic on any surface so that you will have new capability, new processing tools that allow you have rapid prototyping, reduce the cost for your research. And in our speaker talks, they will address the grand challenge in how they apply flexible electronic to areas of energy and bio studies, bioengineering of mapping the brain and other crucial questions that weren't answered without this type of capability. So with that, Lynn is going to introduce our speakers. And
morning. So we have 3 speakers lined up for you today, and you'll see the progression. So the first speaker is going to talk about materials, new materials, and show you some process engineering aspects of making these flexible electronics. And then when we move to the second speaker, she's going to highlight the mechanics of these systems. And then finally, we'll end with a talk that shows you the interface of these organic electronics with biologics. So it's my distinct pleasure to introduce Antonio Facchetti. I've known Antonio for about 10 years now. He's CTO of Polyera. Polyera is a startup company that gives ink-based solutions for flexible electronics, and he'll highlight that. And he's a professor in chemistry at Northwestern too. Antonio?
Thank you very much. I want to thank again the organizer for giving me the opportunity to speak today. Hopefully the view graphs come out. Let's see. Okay, just a second. My fault, I guess. Oh, here we go. Okay, so I'm going to talk about some of the materials we have developed and show you some of the processing really towards making some products. And I cannot show about details of the products, of the material that make the products, because these are confidential, but by mixing some of the things we have done in Northwestern and things we have done in Polyera, I hope to give you a good flavor of what we have been doing. So I'm going to start with a very brief introduction about Polyera, because I'm pretty sure that 99% of the people here don't know about it, and about the printed electronics, at least what is our vision. And I'm going to show you 2 examples of devices that we have used. One, try to enable organic transistors, so all the layers in the stacks are organic. And the application to make a printed transistor and for circuits and for displays. And a second part is about organic solar cell, and particularly using, again, organic material to make bulk heterojunctions, which is a particular type of solar cell, and an example of printing modulus, and some conclusions. So for Polyera, Polyera was started in 2005 from a number of patents that we have developed at Northwestern by myself, Professor Marks, and other co-inventors. We started our efforts in the organic TFT, and then we moved also including some work on organic photovoltaics, and more recently also about solution process, oxide semiconductor, and material for light-emitting transistor, which is a very different technology. We have 2 facilities. One is located in Chicago, Skokie, where we do all the chemistry and the materials development and formulation development, and a second facility in Taiwan, where we do process engineering and customer supports. We have 63 employees, and most of them are in R&D. We have a number of funding sources, and our mission is to not to make the devices. These are our customers. What we want to do is to develop we are a chemical company. Our mission is to develop the new materials, formulate, and teach our customer how to use these materials, because it's such a different technology. So these are some of the area we have touched, and since we are particularly talking about printed electronics, I'm going to mostly work show the results about in these 2 areas. So first of all, how do we see printed electronics? What is our vision? Our vision is for printed electronics the idea is to fabricate part of completely, eventually, optoelectronic devices using printing methodology, additive process at low temperature, instead of high temperature photolithography defined patterns used for silicon and gallium arsenide. This, of course, works beautifully with this material. That's why we have such a great progress in electronics. So how does the two technology compare? For the conventional, of course, silicon technology, excellent performance, high temperature process, works great if you want to make very, very small devices, works great for rigid devices. If you want to make a new fab line, we are talking about between $2–3 billion. So it's great really if you think about a product which has to run for a really long time. You want to really regain this money. For printed electronics instead, we are targeting much less performance. I'm going to give you a flavor what I mean. Low temperature process. We want to print on plastic. So temperature range we are thinking about is about 150 degrees at the maximum. Looking at a large area, printing very fast on large area, flexible devices. We can design the pattern very easily. You can print a newspaper every day. So ideally, you can print the pattern of your circuit equally, with the same flexibility. And here we are talking about additive process, so we do not waste materials. Again, this is the concept. So what are the scientific materials and engineering challenges? One is really to define rules to enhance the performance. Actually, we have learned a lot in the last 15 years in this area. I actually don't have too much concern here. Where the concern starts. First is to develop this material which high performance for roll-to-roll process and using environmentally acceptable solvents. So we have to sell this formulation to people that have been using simply with an AZ photoresist, so which is aqueous base. Start thinking and making them to think about they can use organic solvents. It's difficult in the first stage. So we have to make sure that we have a very safe MSDS for them. We need to maintain the performance on inexpensive substrate and on flexible plastics. We need to fabricate commercial relevant device architecture. Of course, we can prove the material concept on exotic device structure, but then our customer will use only certain device architectures. And it very fundamental is to really understand this charge or light-soft matter interaction, which are well understood for silicon. We use models developed for silicon, but this doesn't mean that they apply in all cases. So for the organic transistor, I just want to show you what are the key components. It's a very simple device. It's a three-terminal device. So you have a source, drain, and gate. This is the conductor. Then you have a dielectric, and you have a semiconductor. So you have all the three materials of electronics. So the way this device works is if you apply a bias between the source and the drain, but you don't have any bias between the source and the gate, the semiconductor has a very low carrier density. So although you have a bias here, you don't measure any current in this current voltage plot. No carrier, no current. So when we apply a bias between the source and the gate, we induce carrier at the interface between the semiconductor and the dielectric. We polarize the dielectric, we induce carrier here. This carrier, if they are mobile, they switch on the device. So you go from the off and the on state in these devices using two independent biases. So you can see the transistors as an electronic valve, which has been great for electronics. So what are the key important factors here? First of all, the carriers can be positive or negative. So you need two types of semiconductors if you want to make complementary circuits. So you need to make both of them. The key important performance parameter is what we call carrier mobility, which tell us how fast this carrier, this is a very approximation, but how fast this carrier moves in the channel. If this carrier moves faster, you can operate with these frequency, these circuits at higher speed. So you can make better and better devices. Also, what is very important in this cartoon is that it doesn't tell the reality of things. The thickness of this device is actually a few tens of hundreds of nanometers, okay? Instead, these distances are several microns. So you really need to think about, you need to print very few nanometer thick film over great uniformity, over meter scales if you want to print in a roll-to-roll fashion. Here, what is really the challenge technically and in terms of process engineering. So if you want to print everything, you need to develop all of this material and need to be able to print nanoscopic thick film thickness of these materials. But if you can do this, what can you get? So these are some examples of devices that we believe can be made in the short term. We're targeting particularly flexible displays and circuits which can drive very simple memories, okay, or very simple memories for sensor type of applications. An example also, this is actually quite neat. Most of the casino chips have an RFID tag inside it. In this way, the casino can monitor who is buying these chips, how much is winning, where is it winning, if they're taking them home, what to do. And these little chips cost about $1. And if they take away, of course, $500 chips, that's okay. The casino makes money. But if they take away the $1, actually, they are losing money. Anyhow, so this is actually a very neat application. But if you can make an RFID, it costs a few cents. That is obviously is not relevant for the casino. But if you can make it for any type of product, you can replace barcodes in your product into something which is printed, and it can be used to track the product and, for example, to pay, to monitor the pressure variation, the temperature variations, where it moved in the store. So this is what we believe it can be done. What is the ultimate dream? This is actually about the video. Video number 1, if it can go on. This is actually sorry, this is not the video I wanted to show. I apologize. I made a mistake. It's not neither the second one. Let me see if I can make it work here, if I'm lucky. Yeah, this is actually the video. Can you just yeah. So if you take a conventional display, and of course it is based on silicon, you can break it. And the idea is to really, and eventually using printing and first organic materials, and then eventually printing to make something which can be flexible, which can be mechanically robust, something you can flex and you can bend. There has been really tremendous prototype, not from us, not by printing, but really try to integrate very simple cell phone with a screen which can expand. It would really give flexibility. This is an example of products that I don't believe in the next 10 years printed electronics can do, but something that material associated to printed electronics will do. Again, I apologize about the video. It's my mistake. So let me go back in the presentation. So I don't have an acknowledgement slides, but this has been important. We collaborated with a lot of people. This has been the people that, I'm an organic chemist actually, where my comfort zone is about these two types of papers, where designing materials and try to understand what are the material properties. But then we had really, besides designing the material, was what has really been important in the field to understand how charges get injected in this electrical contact, how the charges get trapped. At the interface between the semiconductor and dielectric, the mechanisms are very different than for silicon, and really think about different device architecture. So we have really an interdisciplinarity of, and we actually do most of this at Polyera, not led by myself, because I cannot be expert in anything, in everything, but we really, I believe we do all of this, and I want to give you a little flavor. This is only, the first view graph is the only technical view graph I will say related to chemistry, but it's really very important, I believe, for you to understand. So if you want to design an organic semiconductor, there is a key criteria that you have to follow, which are shown here. You have to have a molecule typically which is planar. You want to have the molecule, they stack very, very closely so the charge can move. You need to think about the energetics of the molecule. It has to be at the right place. However, this is not sufficient. This is the example. So we have this molecule, which was old molecule, which can transport charges very, very efficiently, but not in air. So what we have done here, we introduced these red groups, which are cyano group electron withdrawing group. So the band state, the transport energy of the transport bands reduces. So you can switch a molecule from being a good transporter, but under ultra high vacuum, to a molecule which is a good transporter in air. And this is using an energetic stabilization of the molecule. However, if you can take the same core, okay, and you have very little variation in the periphery of the molecule. This does not change the electronic structure of the molecule. It stays the same. However, you go from a molecule which works in air with a very, very low mobility to another molecule which works in air with a very, very high mobility. And this is really related to the morphology of the film. One gives a very bad film morphology. We cannot control it. This second type of film is good, and you can get good transport along the channel. Because, again, we are talking about a distance between source and drain, which is several micrometers. So you have to have a very uniform film throughout the two electrodes. So why this is relevant, and that's why this second type of experiment is very relevant. So we want to print. So if the morphology is important, do we have to control the morphology of this film? And in this experiment, we use, again, this molecule, and we print the molecule between the source and the drain. So here we are looking at the device from the top, and we print in this direction, okay, and perpendicular to the two electrodes, okay? So it's the same film, but we are looking at the transport in two dimensions, two different directions. And you see here, this top film is good, give high mobility, this give a very low mobility. So when we print, it's really important we understand, and we need to design the circuit depending on the type of printing we are going to use, because this will affect the quality of the grain boundaries of the film. This is an experiment where we say, okay, we are developing new organic material, so what is the limit? How much, if everything is perfect, how much can we go? So in this experiment, what we did is, this is a single crystal of this organic molecule. Here there is no grain boundaries, not microscopic grain boundaries. And for this type of experiment, we can say, well, we can get mobility, which is 7, which is not important, the absolute number. We can go up another 1 or 2 orders of magnitude. So this gives us a sort of fundamental limit of how much we can go in the case everything is perfect. These are also type of experiment we do in collaboration. So let's see if this works. So, but what we want to do is printing, and we use different printing techniques. One is what we call inkjet printing, and the concept is very simple. You have a reservoir on top, and you basically eject very little droplets on top of your substrate, like your inkjet printer for inkjet printer at home. And here is an example how I apologize about the quality of the video, but I was not allowed to show others. But, so here what we do, so we have these pieces of plastics where we have metallized electrical contacts, and then we get a roll of this from some of our customers, so we can cut them, and we can start formulating these materials, thinking about different morphologies. I'm sorry, I'm very late. So we need to think about all of this process, and then we start injecting, okay? And you're going to see that, so these are the nozzle, and you eject. And when we eject this, we are going to look at the quality of these drops, how they look like, and we need to tune the morphology of the film. And we do this for different type of techniques. This was inkjet printing. This is another method which is called gravure printing. And here we print using different formulation, and we find the right formulation, which give you the film of right thickness, right morphology, right microstructure for the semiconductor. We do a lot of work with polymers, and this is actually quite neat. So this is a polymer we developed. We cannot eject because the molecular weight is just too long of this micromolecule. So what we had to do is to redesign the chemistry and make the same molecule, making sure we get the right electronic structure, but something we can print. So we really go from a situation where we cannot eject from a situation where we can eject. And this is based on chemistry. We do integration. This is another type of printing. Let me skip it. To do integration, we have to make interconnects. This is very important in electronics, and there is a different way to do it. And here we do it partially by printing. And when we do this interconnects, we really need to worry about, we have already printed several layers. We need to make sure we don't destroy the film. Also, when we put all of these transistors together, this is actually a neat tool. We look at the electrical characteristics, which are important, but also we develop tools to look at the morphology of the film in using a polarized light to have an idea about the dimension of these grains. What is the quality of the crystal, or the grain boundaries along in the sheet of the printed devices. And we do bending tests, of course, and then we put everything together. And if the video number 2 works, which I'm not sure, these are some prototype we made at Polyera, but I'm not allowed to show it, unfortunately. But there is a video which is not this. Can the video number 2? Yeah, thank you so much. So this is basically when you put everything together. These are type of prototype that we don't do in-house, but we do it in collaboration, and you can build everything together. I was trying to explain to my mom how this works, so I apologize. I'm talking, but I want to give you a flavor. So this is actually a reality, you know, for printed electronics. There's printed elements here, something that is not in the previous video. There is no printing, but here there's printed. This is a black and white. I apologize, but let's. All right. So we can go to the next. I think I still have 5 minutes. Okay. So let me skip this, and I want to go to the solar cell. So the type of solar cell we are trying to do it, again, by printing, is what they're called bulk heterojunction structure. And the concept is obvious, everybody understands it, but the way it has to be done in this particular cell, you need to have a blend of 2 materials, a donor and acceptor. So you need to develop, again, 2 semiconductors, like in the complementary circuit type of technology. And in here you need two materials because you absorb the light. The light has to go at the interface between the donor and the acceptor domain, and then the charge gets splitted, and then the charge gets collected to the electrodes. Okay, so you have this process of generating electrical energy from solar energy. So, and one of the important parameters is this PC, power conversion efficiency. Again, here we need the functional material and the thickness are in this range, but you need to print them over very, very large area. So you really need to look at uniformity over large area. So I hope you understand the concept. The type of application is not for grid application. So this is something we don't aim, and we are very conscious as a we have to be less conscious than our customers. They have to be more conscious than us. But we are very conscious that these are not for grid application. At the beginning is really for NIC application, first to understand if the technology works. An example was Sony like 10 years ago when they launched the OLED TV. People thought it was crazy. Why do you want to do this? But I thought that was pioneer, was really try to think ahead. And they demonstrate the technology works. Now other companies are benefiting from it, but the vision was amazing. So what I think here, we need to make very simple devices, which can be very simple, flexible panel, which can be used at remote location, or integrated them on rigid substrate by printing, for example, building integration. These are very simple applications, but will give us a flavor of how the technology responds. We don't do this, so we provide the material, again here, a lot of chemistry we do. We don't do prototyping. This has been done completely at our customer side, but we do a lot of work to try to understand the chemistry, and I want to give you a little flavor. So, as I said, we need 2 components in the bulk heterojunction cell. And why do you need 2 components? The bottom line is because organic material transport charge very slowly. So if you absorb the light and you form the exciton, if the charges do not quickly goes to the electrode, they get trapped, so they recombine. Having developed the bulk heterojunction approach, so having 2 materials, you form the exciton, and then the electron goes into the acceptor region, the hole goes in the hole region, and they have the energetic capability to recombine if everything goes well. So they can slowly, but being somehow collected at the electrodes. So this is an example of a molecule, a polymer we develop as a donor, and the typical acceptor using this technology is PCBM, one of these fullerene type of structure. And again, when we think about developing the materials here, we need to think about all the things I told you for the organic transistor work. But we really need to worry about the energetics and the comparative energetics of the two materials, okay? So it's something that it is an added concern, added things. Because really you need to have a driving force to move the electrons from the donor domain into the acceptor domain and get trapped there, okay? So this is something that is very important. But it's something we can actually design. That is actually still quite easy to design. What is challenging? You need to mix these two, donor and acceptor. Is the morphology of the film which has been quite challenging to control. So you need a morphology which looks like very much like a spaghetti and meatball, okay? Because the buckyball is the ball and the spaghetti is the polymer. You need to have a morphology where you don't have a blend of the spaghetti and the sauce uniform. You want to have more sauce on the top and more white spaghetti at the bottom with a gradient region in between. Because you really need to have domains which connect to the right electrodes to really maximize the charge being separated and not recombined. And I'm Italian, I can make a very good spaghetti and meatball. And I'm sure, Steve, I can beat your mother. But, where is Steve? Okay, so anyhow, so you really need to get this type of we call gradation. This is dead serious. Actually, this is what the holy grail of organic photovoltaics is. I do believe it's not a chemistry. It is really controlling this morphology. And we try to develop tools to understand this morphology gradation. There is some tools which are TM, looking at, for example, here you see you have more buckyball at the bottom and more polymer at the top. We use X-ray experiment. This is a really neat, I think it's a very important experiment and, that actually Lynn developed, is try to understand what is happening at the bottom, at the buried interface. We have a lot of tools to look at the top, right, of the morphology after we spin or we print a film. But how can we monitor what's happening at the bottom? And this is what Lynn really did. And I'm not saying because she invited me here, but I really do believe understand the morphology in this field is really key. And so these are the things really you need to work. So we do think using customer by printing. There's two types of printing. This we call knife coating or slot die coating, which is the most important. And what we do with our material, we can print under nitrogen or air. This is essential. So we know that this type of devices has to be encapsulated. There is no question asked. So the technology has to take into account the cost of encapsulation. But the process has to be done in air. It cannot be done under nitrogen. So we develop material, a polyair, which can be processed in air, which gives equivalent current, not important, these plots, so they give similar performance. We develop blends which are stable over a very long time under encapsulation, under elimination. And this is an example of a panel which was printed by a customer using a certain technique. So with this one, I want to conclude, and I just want to summary very briefly what are the challenging and the opportunity, in my opinion. For printed transistor and circuit, what is actually is really important, and I didn't show it, I'm an organic chemist, is to engineering the process to the main material. Not to make the material in the first place. The tools we have now to predict energy, to predict somehow how the molecule will get closer together. But to try to process, chemical engineering the process and make sure to understand the impurity content which affect the performance. This has not been done. Has not been done for this type of materials. Obviously, also engineering the process, the fab line, again, educate the people receiving the material to a completely new set of materials. And of course, develop the second generation. I show you, I believe we have a set of material which can be used for electrophoretic display for very simple circuits. But if you want to go to a more complex RFID, or if you want to go to color type of display, that is, you need a new set of material. For the organic solar cell, obviously, we need to develop, again, the semiconductor and dielectric formulation. The key challenge is the long-term stability and the encapsulation, actually in terms of enabling the technology, making sure we can encapsulate these devices quite well. What are the other opportunities in a minute? We really have the opportunity to understand new things. So for those of us who does basic science, there is really a great opportunity. What I really believe in is an opportunity which is still fundamental, but it's tremendous technological implication, is tools to predict morphologies. As a chemist, we have tools to predict, to design a molecule, put it in a computer, get a structure out, do the crystal structure of that molecule, and the bond length is accurate at 0.001 angstrom. However, when you prepare a film of that molecule, there is no tools to tell you how the film microstructure will be. This is important for transistor. This is even more important for solar cell, for bulk heterojunction, because you have two components. Okay, so this is very fascinating. Is a project I cannot do. I really don't understand it, but it's a project that I believe is really, really fundamental. And of course, you have the opportunity to make new industries. And with this one, I conclude. Thank you.
Floor is open for questions.
Hi. Thanks for the very interesting talk. Philip Fun from Case Western. My first question is, in your pristine single crystal experiment, you show mobility is 7. What's the fundamental limit of that? It's because this is still like 2 orders of magnitude lower than silicon. And second question is, in the devices you show in the video, what are the pixel size and what are the resolution? Do you have a roadmap for the device technology?
Yeah, I mean, for the second question, I cannot comment about specific about that type of display. I showed you some specification. Our goal is to make a very first type electrophoretic. This is what our customers are trying to do now. We are in fab line to make a 6-inch type of electrophoretic display, which has a bending radius of about 1 centimeter square. 1 centimeter. So this is one of the key requirements. You can, in terms of resolution, like a sort of first-generation Kindle is what we are targeting at the moment, that type of quality and speed in the response. For the fundamental work, maybe I was generalizing because I was saying too many concepts at the same time, but you can use single crystal to have some answers, okay? You say, okay, I have this molecule, I made a single crystal, this is what I get for transport. However, this device is very complex. You have a dielectric, you have electrical contact, all of these affects the mobility. So I didn't talk about that second part. You can use the same single crystal and you put it on top of a better insulator and the mobility is 10 to the minus 5. And you put it on top of a much better insulator which can fill traps at lower voltage and you get either higher, better characteristics, doesn't mean better mobility. So we used this single crystal experiment more to give us a figure of merit, okay? If we use this molecule with these substituents, typically we use a dielectric as a PMMA, so a polymer dielectric. As electrical contact, we use silver. These are sort of very close to what we do in manufacturing in terms of combination. This is roughly, we get about 7. We get about 10. We get about 0.1. So it's more to give us a flavor of where we can go. It doesn't mean that this is the ultimate limit for this type of molecules because it depends on, and it doesn't mean that it's the ultimate limit for organic transistor. There is an example of single crystal molecules which gives mobility about 30, 40. People have reported for anthracene, a very low temperature mobility of 60, 70. So these experiments are more for us to, how much can we go if everything goes perfect? But there's a lot of things going on.
Hi, Robert Worrell from Boeing. I personally have worked on a number of projects at Boeing using direct write technologies and trying to further the application space for those. And specifically in the area of multifunctional structures and high-frequency electronics, a lot of the limitations that we ran into with the current direct write technologies and the ink systems were kind of twofold. First of which were cure temperatures to achieve quote-unquote high conductivities and then the relatively low conductivities of the existing inks. And I noticed you didn't discuss any of the conductivities of your conductors. I was wondering if you could comment on that as well as the curing environment that they must go through.
I mean, this is an excellent question. I did not comment on that. I mean, we are not working on conductors, and we are not. I didn't comment in this specific talk because it's not relevant to our customers. What it limits the technology at this stage are not the conductors. For this product I just showed you. Obviously, if you are going to go to RFID card, working at 13.5 megahertz, there you need to worry about also parasitic capacitor, the conductors, how much you lose. But for very simple electrophoretic displays, this type of technology, the conductivity of printed metal, and typically silver. Now there is an excellent silver precursor that can be printed. They can be converted about 120, 130 degrees, and they have excellent conductivity. So it's not limiting our customers' product at the moment. But it, of course, is important when we go to the next generation of product.
Hey, Mandakini from Xerox. So I have like two questions. First is like, how can we control the morphology, you know, because this is the most important part in the organic solar cells, right? Now, because the change in morphology changes the charge generation, charge transport. So this work is going on for last 5 to 10 years, 5 years at least, I think, because I follow the papers and I have also worked on this area. But how to get the same morphology in each of your fabrication process? Because when I was working and I do the fabrication every time, you know, to control the morphology is a big problem. So my second question is more general. My second question is like, how can we attract the industries, you know, like the big industries to play a role in the flexible electronics? How can you, what is your path for that?
Yeah, those are very important. So for the second part is how do we convince them? We convince them if someone starts making money. If that is it's a very fundamental question. And I go back to the Sony. I mean, Sony spent a huge amount of money. I mean, Kodak spent a huge amount of money. They invented it. So, but they didn't make any money. And so there is always a transition in the technology. So how do we convince new customers? We need to convince the first couple of customers to make product, and hopefully these products are going to, and this actually go back to your first question, is that related to your question. How do we get the morphology control all the time? We need engineering. The field has been boosted somehow by mostly chemists and, you know, people putting together. But nobody really ever made 50 liters, 100 liters, 200 liters of one formulation. There is only one formulation. And you change all the other processing and see how does the morphology change, how the performance change. So nobody has done it. How can you do this? You need to have someone who is committed to provide these formulations. And we believe we are committed. We really spent resources in doing that. We need to have someone committed on the other side to accept advice how to use this formulation. Because typically, at the most in fab line around the world, people are using a photoresist and something which removes the photoresist, which is an aqueous base. So you send a formulation and start smelling a little bit like almond, for example, and these people, they just get scared. I don't want to touch it. I don't want to smell it. I'm afraid. So first of all, it's a culture to do that. And then after we convince them, they are developing tools. And for example, I show you an optical image of the crystals, okay? That is very important. We have to develop a tool to look at the crystal. It has to be a polarized light optical tool. And we need to measure this crystal, and we have to make sure this crystal has the same size over a 20 centimeter square substrate for one batch, and then we have to go for the different batches. So I hope in order to do it, we really have the help of engineering who really knows exactly how to change in the process and the customer side.
Hi, I'm Mina Rice at the University of Michigan. Thank you. It was a very good talk. So can you also comment on the leakage current, and if you're also working on the materials for the source and drain to make sure that the junction potential is higher to the semiconducting channel?
That's really also another very good question. Polyero was started in 2005, and we had the very first meeting with the customer in 2006. And we sat there and we started talking with the people like me. And then the top executive came down for just 10 minutes, and he said, I want to have a presentation in 5 minutes. You have to summarize what you've been talking for 2 hours. So I show, and I said, we were working on the semiconductor. At the time, I was very naive. I was working on the semiconductor, changing the structure, working on the dielectric. And this person said, why are you working on the dielectric? I mean, these are all like, we can work with dielectric all the time. No problem. Well, now this customer does not exist anymore, but the dielectric is what it limited, actually, the products. With the morphology of the semiconductor is being the dielectric, because really get pinhole free over this area, and for display you kill few transistors and your display does no longer work. Has been, so we developed the dielectric that they work. You need the right leakage, you have to have a picoamp. It has to be the same over, the 20 volt SWIP, and it has to be printable. It has to be to have all of these type of characteristics. So it's really been part of developing the technology, and also what it limited the technology at the beginning, because many people at the beginning, the vision was so great. The vision was, okay, people are starting getting laptop and a computer, so that we are printing less and less newspaper, we are printing less and less magazines. So the concept was, okay, let's use this printing machine, this printing warehouse, and start doing printed electronics. We can print conductor. We have been printing we are printing conductor forever, so we can do it also. So we lost time because we tried to do this in a jerky environment, so we draw a lot of wrong conclusions. And most of that was related to the dielectric. So if you have a pinhole in the semiconductor, it doesn't matter. But if you have a pinhole in the dielectric, it will kill the device. So it is I didn't have time to show the dielectric, but is the second material which limits the technology. It was limiting.
Great. With that, let's thank Antonio for an entertaining talk. Our next speaker is Nanshu from University of Texas at Austin. So Nanshu and I have two touch points, although we haven't met each other until this conference. So Nanshu and I actually worked for the same postdoctoral advisor, never mind 10 years apart. And Nanshu's now at University of Texas at Austin, and I was there for 5 years before I moved to Princeton. So.
Good morning, everyone. I would like first to thank Tina and Lynn for giving me the privilege to present in this very prestigious symposium. And today I would like to share with you a very thriving field of biointegrated electronics. I will start my talk by talking about the motivation and some grand challenges in this field. And I will selfishly talk about something related to the mechanics, which is always behind the scene hero, but we can apply some fundamental principles in mechanics to really help the development of flexible and stretchable compliant electronics based on even very brittle, very fragile ceramics like silicon. And I would like also, another purpose is to try to entertain the mechanical engineers a little bit in this symposium. And I would like to show some very entertaining examples just to give you an idea of the potential, the capabilities of this enabling technology, and end my talk with some outlook of the field. So first of all, whenever we talk about biointegrated electronics, we start to think about health-related devices. Health monitoring, for example, surgical tools, those are minimally invasive endocardial balloon catheters, and implantable devices. And the health medical device market is now over 300 billion, and it's growing every day very fast. So of course, those are all biointegrated devices in electronics, and we hope to make them better. So another very major field for both research and intelligent robotics, human interaction robotics, is the human-machine interfaces. Here we have two German scholars trying to talk to the computer, how are you? And we also have assistive devices for disabled people, or even try to augment the natural capabilities of human beings. So, however, I'm a mechanician, so whenever I look at human body, I would like to describe myself like soft, resilient, and curvilinear. None of the part is really perfectly flat, and timely dynamic under constant motion. However, modern electronics doesn't take that route. Every mechanical property is exactly the opposite than this. All right, so our skin and the wafer-based silicon has a stiffness mismatch of over 6 orders of magnitude. And our skin can easily stretch by 15–20%, whereas silicon breaks at 1% elongation. Silicon is perfectly flat. The smoothness, the flatness is actually a high criteria, and it's very rigid. It cannot be deformable in any way. Because of this big mechanical mismatch, state-of-the-art electronics look like this. Of course, do we really want, none of us like sharp pins going into our brain, rigid boxes embedded in our muscle. We call them chips on tapes and bricks on straps. And we want to make things better. And what are the actually desired properties of those bio-integrated electronics? Well, in terms of mechanics, we hope to have conformable, stretchable, compliant systems that can actually bond to our tissue, either on the skin or internal organs with very robust adhesion. Even when we are moving, they do not detach very easily or cause any kind of slippage or relative motion, because that's very critical for the signal data acquisition. In terms of materials, we hope them could be very high performance. It's health related, it's life dependent. And we hope them could be biocompatible, of course, and even in some cases bioresorbable, meaning that they could be implanted and be absorbed by the body without doing another procedure to take it out. In terms of functionalities, we hope, because on our organs, the real estate is still limited, we hope to integrate miniaturized devices that could perform multifunctional tasks, so that we can use one integrated device for a lot of purposes. In terms of cost, power, weight, and size, of course, we always want to minimize them. They are not fully met. Those requirements are not fully met by now, but we have been working in this field very hard to meet those goals. So first, I would like to give you a very simple flexible electronics cross-sectional layout to show that we have polymer substrates, which is used to support those high-performance silicon inorganic electronics, including very brittle silicons, multi-layer metals, dielectrics based on rigid polymers, or even dielectrics, oxides or nitrides. So for a system like this, in terms of mechanical properties, we could categorize those type of electronic materials into 2 types. The first is those metal family. They are known to be ductile material, but actually when you are talking about thin film metals, they actually could only elongate by about 3 to 5%, and they rupture by necking, by strain localization. However, when they are supported by polymer substrate, the hypothesis is that the polymer can help retard the strain localization because they can provide a good constraint if the adhesion is good. And eventually, if the film detach, they rupture again by strain localization. Now, once they detach, they have the room to do so. In terms of silicon oxides, nitrides, that's another family. That's very brittle, very fragile materials. And in this case, they fracture by very sharp, very clean cleavage cracks. And this kind of brittle fracture, the polymer substrate actually does very little to prevent that. And their failure strain is very, very small, only 1%. So how do we address those basic challenges by using thin film mechanics? Well, this is the first experimental picture to show that, to validate the hypothesis that actually metal thin films does fracture from polymer substrate by by the co-evolution of delamination and strain localization necking. So actually, I want to also take this opportunity to thank DuPont, because I constantly request samples from DuPont for Kapton, and they are very generous to support this small amount of academia research without charging us. And using this, because we know this is actually the failure mechanism, now all we need to do is to really make the film softer so that there is less driving force for delamination, and also make the interface stronger by adding an adhesive layer, very high performance adhesive layer. So here we can see that the film without adhesion, without post-annealing, easily fracture at about 10% elongation. This is the resistance change. And when they deviate from this theoretical prediction, that denotes the micro cracking. And we do see a lot of micro cracking at about 20% elongation. And when we have very good adhesion and very soft film, we see only a very gradual increase of resistance with the elongation. And that's purely due to geometric effect. There's no micro crack even after 60% elongation. And of course, this is a blanket film. And for blanket film in the past, the fracture strain is only within 10%. Now we have increased the stretchability by 6-folds by knowing the failure mechanism. And then in terms of brittle materials, I want to review a very simple concept even chemical engineers could understand, I hope. So if we take a look at a uniform beam, when we try to bend it, we can appreciate that actually the top surface of the material is under tensile strain, positive tensile strain, and the bottom surface is under compression. And the maximum strain on the top surface, the tensile strain, is proportional to the bending curvature and the thickness. And for brittle material, the critical failure strain is usually less than 1%. Therefore, the maximum strain cannot exceed 1%. Otherwise, it will just crack at the top surface. Therefore, if we can reduce the thickness of the membrane, we could enhance the bending curvature by orders of magnitude. It's just because of this very simple mechanics concept. And if you don't believe me, let's take a look at bulk silicon wafer, millimeter thickness, very hard to bend or curve. And when we reduce the thickness to micron regime, they start to become bendable. Down to nanometer regime, they are super bendable and it looks like ribbons, even curl under their own internal stresses. So this is an illustration, a demonstration of the overall structural behavior not only depends on the intrinsic material property, but also depends on the shape, on the geometry of the structure. So then how do we transfer this kind of bendability to stretchability? Well, a very smart idea not developed by me is this buckled ribbon idea. So scientists put flat silicon nanoribbons onto pre-stretched rubber substrate. They bond them well and they relax the substrate. So once upon the relaxation, rubber substrate is very elastic. It can contract back. But the silicon ribbons are very stiff, very thin, and they take this out-of-plane sinusoidal buckling mode to minimize the overall elastic energy. And this is an instability mechanism which involves large displacement but very small strain. And in this case, even though the substrate could be then repeatedly stretched and compressed by over 100 times, the intrinsic strain, the interatomic distance in silicon atoms are less than 1%, far less than 1%. And of course, a 2D version involves the pre-stretch of the rubber by biaxial. But nowadays, because those pre-stretch of substrates is not very microfabrication friendly, so this becomes a more popular scenario where instead of using continuous silicon membrane, we chop them up into isolated pixels of silicon islands. Those silicon islands are much, much stiffer than the substrate. And we can fabricate all sorts of inorganic transistors, diodes, sensors on top of rigid islands. They provide a very rigid support. And then the inter-island portion, because they are rubber, basically, when we stretch, they can stretch enormously without leaving any noticeable strain in those rigid islands. And of course, if we want to build an interconnected circuits, we still need interconnects. And instead of using a straight metal wire, now we use a serpentine metal wire. We call it meandering shape. So because of then, again, geometric change, we could accommodate enormous, very large applied strain over 100% without, again, intrinsic strain, introduce the lattice constant change in this kind of even metal. And of course, we know that in all of those cases, the serpentines actually has a sandwiched structure with metal in the middle, and polymers try to provide that kind of constraint to even enhance the stretchability. Well, the geometry dependent could be carefully characterized by mechanics, and we have developed theories in my group to now try to optimize the shapes of the serpentine, and then try to even look at the out-of-plane buckling, the effect, so that we can even enhance the stretchability. Of course, this is finite element modeling, numerical modeling, and now we're even trying to develop theoretical modelings for these systems. And the overall goal is to apply this system not only to metal, but also to semiconductors, to inorganic materials. And we do experiments in our lab, and we can achieve over 1,000% stretch for metal structures like this, and over 100% stretch for silicon structures. Remember, the intrinsic factor of strain of silicon is only 1%, a 100-fold increasement. Okay, so in terms of silicon islands, people would like to actually use this very stiff Kapton substrate for a lot of printed circuits because it's very robust and easy to handle compared to very soft rubber substrates. So in this case, if we have brittle, fragile ceramic islands, either silicon or silicon nitride, after 0.8% stretch, we see full of channel cracks, and of course it could even have delamination, all those difficulties. But people still like stiff substrate, okay? They don't just like a rubber, very floppy substrate. So our solution is to add a very thin but very soft interlayer between the stiff substrate and the rigid islands. So we build shear-lag models to account for the large shear strain that is capable for the soft layer. And because of this decoupling effect, strain isolation effect, even if the substrate is stretched more than 19%, the islands still remain intact. And of course, if we stretch more, the soft substrates gives us complications like transverse wrinkling or channel cracks. And because of actually, I also saw the DuPont engineer yesterday during the poster session that in their solar cell panels, they are also using this exactly the same mechanism. Instead of using PDMS, they are using EVA, very soft membrane, and those are silicon panels. And they have PET substrate, which is stiff. And by doing this kind of strain relaxation, they could also achieve very good flexibility. And of course, beyond solar panels, just for very general examples, that principle could enable scientists to now fabricate electronics on all sorts of very stiff but flexible substrates, including fabric, vinyl glove, printing paper, aluminum foil. In all of those cases, there is a very thin, transparent, soft layer between electronics and substrate that you cannot see. They are transparent. Well, so those devices are fabricated by using a microtransfer printing technique because high performance, high quality single crystal semiconductor membranes are hard to fabricate just by deposition, and we can easily have them commercially available. We retrieve them from the donor substrate. After we do all the high temperature processing, doping, things like that, we retrieve them, print them onto a receiving substrate, still rigid, so that all the subsequent fabrication procedures are fully compatible with current IC industry. Patterning of silicon, metallization, spin casting, photolithography, very standard procedure. And we etch them, again, using RIE, very standard. And the last step is to transfer them from the rigid handle wafer, which is just dummy wafer to provide mechanical support, and then print them onto flexible substrates. And in this procedure, it's very rich of mechanics because think about when we try to print, when we try to retrieve, we hope the adhesion between stamp and the membrane is good. But when we try to release, we hope the adhesion between stamp and membrane is actually smaller than the receiving substrate. So there are a lot of freedom we can play. And here I just want to demonstrate some examples of applying those basic mechanics concepts, applying this very advanced microtransfer printing technology, and fabricate health-related devices. And I break them into two categories: non-invasive, which means skin-mountable wearable devices, and in vivo, which means inside the body. So first of all, when we try to mount something onto the skin, again, I look at the mechanical performance. Relatively stiff and thick polymer, it can still conform to my wrist, but once I deform, they detach very easily. Whereas when we reduce the stiffness, reduce the thickness, even by not changing the interface, none of these have any adhesive on the interface. Pure van der Waals weak interaction. Because the driving force is low, the delamination didn't occur at all. Of course, this whole system could be experimentally measured by a more rigorous configuration and modeled. And the lesson we learn here is that we need to make electronics thin and soft. So in order to make it soft, the island plus serpentine structure is still about 5 times stiffer than our skin. And I eliminated all the islands because there is no intrinsic limitation for me to fabricate those sensors, transistors, into serpentine meandering shapes. There is no fundamental limitation. This system, compared to a pig skin I tested, is even the overall effective modulus is even lower than the skin. We have created the world's first truly skin-like, in terms of mechanical property, electronics. And in terms of the stretchability, I tested just about 30% because by all means our skin will start to have failure after 20% strain if we stretch the skin. Even if one day I want to do facelift, I know my limit. So in this case, the intrinsic strain, again, interatomic distance change is only about 0.15%, far below the fracture or yield strain of our inorganic materials, even after 30% overall strain. And then if you want to fabricate something very thin, very soft, this is how they look like. Okay, they will crumble by surface forces, by electrostatic forces. Therefore, we come up with the idea inspired by temporary transfer tattoo, that we have a temporary supporting layer and we can remove them once we put them onto the skin surface. And this is a video to show how our devices look very flat, very easy to handle and transport. And when we target the position, we just smear water on the back surface so that we can remove the temporary, very stiff water-soluble layer, and left with all the electronics, the sensors sandwiched between the rubber membrane and our skin. And the whole system has the stiffness as small as skin, and they do not require any kind of bioadhesive to adhere to skin, pure van der Waals interaction. And they do not have any relative motion with the skin. That's the most important. Thank you. And then when we try to remove them, because we didn't apply any adhesive, the removal is very easy and smooth without causing any redness or loss of hair. Okay, not like the Band-Aid. But it is a one-time disposable tattoo, and it can be worn for over 2 weeks without any problem, and then the natural exfoliation of your skin will take it off. Take a microscopic view. We could see our filamentary serpentine meshes. They could be either metallic electrodes or even the silicon transistors. And they can conform really to the finest wrinkles of your skin and form this very intimate contact, which is important for the interface impedance, and that will contribute to very high signal-to-noise ratio. Even without using an amplifier on site, we're able to get fairly okay electrophysiological signal. Here is an example. There's no amplifier on site. We still have wires for data acquisition. It's a passive device. No battery is needed. And we can, when we speak up, down, left, right, we can measure the electromyogram from the neck muscle. And the waveforms are apparently very distinguishable. And we build a library of them and do pattern recognition in the future when you speak them again. And we can recognize what you are trying to say, not through your voice, but through the EMG of your neck muscle. And of course, you have full of muscles on your body, and you can think about controlling robotics. And this is just one demonstration. There are many other thin film, low profile devices that could be readily integrated onto this platform technology. I'm not going to go to all the details. Well, instead of printing onto a tattoo, where else could we print? I could print onto a silicone finger tube molded out of a hand model, and we're trying to use this system to mimic the mechanical braille patterns that blind people are reading. And in these cases, those 2x3 arrays of electrode pairs could stimulate the neurons on your fingertip to create something called electrotactile sensation. It's electrical, but it feels like something is poking you. And of course, there is a desired voltage and frequency domain where this could be functional well. And as an in vivo example, I don't have much time. I just want to show that we can then enable we can show the extreme stretchability of our devices. Previously, we showed extreme compliance of our devices. State-of-the-art balloon catheter technology used by cardiologists are purely mechanical manipulator. There's no active devices on them. When cardiologists want to have sense some endocardial information or deliver some endocardial therapy, they use this kind of single lead catheter and do dot-by-dot preparation. And therefore, we could instrument a commercially available balloon catheter by our devices and perform in vivo animal experiments where we could measure the contact, because this is all they could see currently under X-ray. We don't know if the balloon is in contact or not. We don't know the temperature, but here with the temperature sensor and with the electrodes being used as the ablators, we could create a lesion to stop the arrhythmia and measure the temperature while we are doing the ablation. And that provides very valuable feedback to the surgeons. And a last example is a very soft strain gauges that is not available to soft materials for over a long time. And people have to use imaging technologies, MRI, X-ray, to really see how tissue mechanically deform. And with this kind of soft strain gauges, those strain sensors are still very rigid, piezo-resistive silicon, but they are sitting on a soft substrate and engineered so that the whole system could be very stretchable. And we could use that, laminate over the heart, and measure a healthy heart versus a heart undergoes ischemia, where the heart loses blood and stiffens its muscle, its tissue. And the beating amplitude can be reduced significantly. And this is the first demonstration that heart ischemia can be, the onset of heart ischemia can be measured by quantified strain gauges. And here I just want to conclude my talk to really show you that we have worked mainly in this regime where we have enabled bioelectronics integration, adhesion, and then there are a lot more for implantable adhesion on wet surfaces. We haven't touched much about the biochemical interface, the thermal interface between bioelectronics. Those are very rich areas to work on. And of course, in terms of power and data, they remain the biggest challenges to enable really wireless, wearable electronics for health-related purposes. With that, let me thank my postdoctoral group, where I thoroughly enjoyed the research in this field. And on my current group at University of Texas, they are a wonderful group, constantly challenging me. And we do have water and lake in Austin, and ducks. And I want to thank our sponsors and my collaborators. And of course, thank you all for your attention.
Questions?
Hi, a very interesting talk. I really enjoy. Thank you. It's Alberto from IBM. I wanted to get some clarification from you regarding the applications and the challenges from those applications. Something that I found, and this is my understanding, so the question is, correct me if I'm wrong.
Okay.
Something that I found a bit, that could be a bit misleading about one of your introductory charts showing like this large electronic something with a band and everything is that my understanding is that the amount of functionality that you can integrate in an IC, it's incredible. You can have full transmission, reception function, memory, digital DSP in something that you could barely see. So in terms of active integrated functionality, you could take a very, very small IC, very thin, and then somehow glue it, and that wouldn't need to be flexible. Mm-hmm. What I think is the challenge is in the, I would regard this in terms of electrical engineering as the packaging, the flexible packaging and integration of the components that truly need to occupy a large area, truly need to occupy and truly need to be flexible. For instance, an antenna in case you want to use lower frequency, or some distributing sensor, or the application here for the voice, which I thought was amazing. I didn't know about that. So is that understanding true? Is there a need for true flexible transistor, or is it more just on the integration of something we can do very small in silicon with other components?
Thank you. Thank you very much for the very intriguing question, very fascinating question. And the answer is for a very small area, yes, temporarily for short term, we could use the state-of-the-art integrated circuits, very miniaturized, and mount that onto our skin. But first of all, you will need bioadhesive. And secondly, those adhesives either irritate the skin or doesn't last long. And they are not mechanically compatible with the skin. Therefore, we have the chance of losing them if we deform too much. And with that being said, I do think the immediate step of wearable soft electronics is to have the sensor part flexible, stretchable, and have intimate contact with skin. And leaving all those microcontrollers, batteries, ADCs rigid and form in a flexible band. And the band could be releasable, reusable, and the tattoo is just adhered. That's my vision. And eventually, of course, for the far future, ideally, everything is soft as skin. It's like a secondary skin. You never feel about it. You don't realize you are wearing it. We can use camouflage to cover them by actual tattoos so that no one else could see it. But that's the far future, everything stretchable. Yeah, thank you.
Hi, Pablo Valke, Weilinger Associates. I have a question about the in vivo application. So it seems perfect to me for the outside application on the skin, but once you get inside, do you have to worry about the life cycle? And specifically when you start stretching the device and serpentines actually start buckling out of plane, they cause local disbonds away from the substrate. Mm-hmm. And then you keep actually stretching, and it's a cyclic type of load. So eventually that disbond is going to propagate and disbond entirely from the skin. And also just the local disbonds, stop sending the signals that you want. Mm-hmm. So, and then if it disbonds completely, what do you do with it? Do you have to worry about it? Do you have to go in, surgically remove it? What is the life cycle? What do you do with it long term?
Yeah, thank you. Another biggest challenge in this field. Let me clarify a little bit, because our devices so far are only applied for short-term surgeries, not for long-term implantation devices, because we don't really have embedded power supply for that. So you are perfectly right that with those kind of designs, they sometimes detach from the substrate, but we have ways to fix them by sandwiching them between the tissue and a rubber layer which attaches to tissue perfectly well. So the serpentines only have in-plane motion instead of buckling out of plane. And their cyclability are extremely good, because the maximum strain when we stretch to the maximum is only about 0.1%, which is much lower than the critical strain. So the cyclability, we don't worry that we have tested it over 10,000 cycles without any issue. But the biggest challenge is the encapsulation of the electronics over long term for implantable devices, because we don't want to shock the person or the animal, or we don't want the conductive biofluid to compromise our devices. So encapsulation is always challenging.
Widon Song from Boeing. Nanshu, good job. I'm really inspired by your research work.
Thank you.
I think probably Antonio or maybe feel a little bit pressure from your research, although I'm sure he still can beat you on making Italian food.
Don't stimulate him.
All right, I have a question on the stretchable strain gauge. That can be very valuable for us to collect real-time diagnostic data for critical aircraft structures. I want you to know more about the technical readiness level for this technology. Can you shed a little bit more light on that? Thank you.
Yeah, sure. Thank you for another very important question. It's important because we are using piezo-resistive silicons. Silicons are known to be very piezo-resistive materials with intrinsic gauge factors over 200. As much as 200. But when we integrate that onto soft substrate, we are talking about the overall gauge factor, and because the strain transfer from soft substrate to rigid silicon is by all means very small, because we want that in order not to break silicon. But because of that, the gauge factor is lowered down to 0.2.3, which is actually lower than commercially available rigid strain gauges, metal foil based 2 to 3 gauge factor. But the story is that if you want to measure the soft deformation of soft tissue, soft rubber, or other soft materials, even gels, you do need this kind of system level compliance to do that. And for structural health monitoring, actually that's a different story, because the substrate now is stiff, like the plane wings and things like that. So rigid conventional strain gauges could work. The problem is that you have to address them one by one, put them, deploy them one by one. And then the beauty of flexible or stretchable electronics is that we can fabricate devices on just a 6-inch wafer, very small, very limited size, and we deploy them 10 times, 100 times, 1,000 times over very large areas, like a net, like a web, so that we don't have to address them one by one. They're all interconnected. They're all ready to go. So that's the beauty here. Yeah. Yeah. Ah, I see. Yeah, they are still stretchable because their interconnects are still stretchable as long as we don't stretch to the absolute maximum. Yeah.
Ash Peterson from Medtronic. Very interested to hear about your stretchable electronics there, specifically in implantable devices. I'm just picking up on another question, on a previous question related to the fatigue performance. You mentioned approximately 10,000 cycles. Do you have any feel for ultra-high cycle fatigue? You know, we're talking hundreds of millions of cycles, not 10,000 from an implantable device. Thank you.
Yeah. That's very important for like a constantly beating heart applications, or in some civil or aerospace engineering applications. And the answer is I don't know, because we have never tested it over 100,000 cycles. But what I can say is that as long as we can keep the maximum strain much lower than the critical strain, then the lifetime is very high. And if it couldn't meet the requirement, we could engineer and even make it lower so that the lifetime will be extended as we lower the strain.
Okay, just a follow-on question. So do you have a feel for how low that is? Because at least in our experience, you know, just lowering that strain,
So now,
is it necessarily your answer?
Oh, so what kind of failure do you observe? Fatigue failure, yeah. But in our case, the maximum strain is at most 1/10, 10% of the critical strain. And we can even lower that by engineering the shape to be more tortuous and softer. Yeah, it's about 10%. Of course, if you approach 90% of the critical value, then probably the cyclability is only 100 times. Yeah, so there is this game we can play.
Hi, Robert Worrell from Boeing again. In the research that I've done and the applications that we've worked on, one of the real holy grail processing methods is direct write, and being able to have that circuitry be printed directly on the thing that you're wanting to do the sensing or whatever you're wanting to do. And there's been a lot of progress in that and using the structure as the substrate. But in a lot of the medical applications and a lot of the discussions so far, that's been the substrate is some other carrier substrate that's then applied to the ultimate application. I was just wondering what your view is, if we'll ever be able to get to that point where we can directly print semiconductor devices on like a biological substrate.
Yeah, definitely. I do think it's definitely possible. It's just a matter of time. As a demonstration, I didn't show the video, but very recently coming out of Professor John Rogers' group at Illinois is that instead of using the tattoo substrate, they could directly print the fabricated substrate onto human skin by just spraying a little bit of liquid bandage as the adhesive. That's off the counter, $3 you can buy, and really fascinating, saves a lot of steps. And of course, that's just a shortcut because we're still fabricating all the devices on the wafer, and that's just a final transfer step. So in terms of direct printing, I think the problem so far is really the biocompatibility and the manufacturing equipment. So of course, a lot of those printing technologies I talk about today are already automated. But of course, on wafer, it's so easy. It's just the machinery. But on biosystems and people make like scaffolds and all those tissue engineering, much more complicated. And that's why we really need to bring all the expertise from mechanics, electronics, material science, and medical and biologists. And also I want to mention that actually the mechanics we're talking about here, although I apply them mostly to inorganic materials because it's magnificent, but we could also easily apply that to organic materials. And actually, Antonio, I saw a picture of yours full of cracks. You skipped it, but I saw it. So organic.
Okay.
Organic.
Well, I wanted to show that what is good and bad.
Yeah. So what I try to say is that organic electronics are fascinating, low cost, large area, definitely, and the fabrication is much easier. But some of the organic polymers are actually still pretty stiff and rigid, and the same mechanics easily applicable.
All right, with that, let's join me in thanking Antonio and Nanshu. We have a break now, and we'll reconvene at 10:45 for Polina's talk.